Hello again, and welcome to Advanced Physics for High School students. This is Lesson 48, and it is entitled Magnetic Fields. We are undertaking now a topic that is very rich in its application in modern society, also rich with things to know for the AP exam. Magnetic fields vary from things that we hang on our refrigerator to remind us about important dates or people who are important in our lives. They are found in electric motors, loudspeakers for our sound systems. They're found in hospitals for magnetic resonance imaging. They're part of basic research, like at the European Center for Nuclear Research, CERN, on the border between France and Switzerland near Geneva. Magnetic fields surround the Earth and are used in navigation. This topic is a very important one, but it's also a very complex one. What we want to do in this lesson is to lay some groundwork and begin to get into a quantitative analysis about magnetic fields. So whether you've played with Woolly Willy, with iron filings and a magnet, and entertained yourself, or whether you are interested in solving some complicated problems, we all begin with what we already know. So let's list some things, either about what we already know or some basic qualitative ideas about magnetic fields. Historically, the word magnet comes from the place where stones that attracted other stones were found in Asia Minor in a region called Magnesia. In English, we call these magnetic stones lodestones, and in fact, there are some samples that we have in the classroom that perhaps we can lay our hands on sometime, give you a chance to see what they're like. If little pieces were broken off or a piece of metal, a thin piece of metal were rubbed against these stones, it was found that if those thin needle-like pieces of metal were allowed to align themselves, say suspended from a string or maybe floating on some water or something like that, that they tended to align in a north-south direction. And so it seemed logical to call the part of the needle that aligned towards the North Pole, as in the north geographic pole of the Earth, the north-seeking pole, and the other end to call it the South Pole, and that's what we call a compass. Whenever you see arrows associated with magnetic fields, then you should look at the tip of the arrow as the North Magnetic Pole and the tail of the arrow as the South Magnetic Pole. And these little compasses can be used to look at the direction of magnetic fields, whether it's from the Earth or whether it's from some other object that's creating a magnetic field. Now, it's found that if you put several of these pieces of rock together, or compasses or bar magnets, that opposite poles attract and like poles repel. So for example, if I have two bar magnets, as shown in this diagram here, and I put them close to each other, those two magnets are going to feel forces. So the magnet that's on the right-hand side is going to be pushed away from the magnet that's on the left-hand side. On the other hand, this second pair of magnets, where you could imagine I've taken the right-hand magnet and turned it around, these two magnets would experience an attraction. So there's a force that each of them feels. The one that's on the right gets pulled to the left, and the one that's on the left gets pulled to the right. People observed this a long time ago and tried to have some understanding of it. It turns out in our modern understanding, we say that the source of all magnetism is moving electricity. That's a very important statement. You need to write it down in your notes. I'll say it again. The source of all magnetism is moving electricity. That fact is one of the most important facts that you can remember about magnetism. And if this connection between electricity and magnetism was something that was discovered only within the last couple of 100 years. Before that time, it was thought that electricity was a separate entity than magnetism. And so people were doing experiments like Benjamin Franklin and looking at electricity. There were other people who were doing experiments with magnets, and in the early 1800s to mid-1800s, a young fellow Englishman named Michael Faraday discovered, almost by accident, a connection between those two. Actually, he was preceded by a Danish fellow whose name was Hans Christian Ørsted. And Ørsted noticed that a current that carries a wire could twist a magnet. Faraday started to work with electricity and magnetism and accumulated this bunch of observations. And then later in the 1800s, his young friend from Scotland, James Clerk Maxwell, put together the mathematics that united electricity and magnetism. So this is a big unification, and you will hear people talk about Maxwell's equations. I'll jot these names down here just quickly so that you'll have something to hang your knowledge from. These three gentlemen, Ørsted, Faraday, and Maxwell, did many other things besides the work with electricity and magnetism. But Faraday is the one who first ferreted out the connections, and Maxwell was the one who put them on the mathematical foundation. We know Faraday from his work in many different areas besides electricity and magnetism. Maxwell did work with thermodynamics and gases. The electromagnetism is one of his greatest accomplishments. So now, if I take a bar magnet and I take some iron filings and I sprinkle those filings around the bar magnet, it turns out that there's a pattern that's produced. And that's what this figure shows. There are some iron filings that are here and some small compasses, and those iron filings seem to trace out lines. These iron filings line up around the magnet along something called lines of magnetic force. They trace out the shape of the magnetic field around the magnet. Let's imagine for the moment that the left side of this magnet is a north pole and the right side is a south pole. There's no indication of that on this particular magnet. We can imagine that for the moment. If that's the case, then these small round compasses that are there show the magnetic field lines. We could draw them as arrows around this magnet. Remember that the tip of the arrow represents a north magnetic pole and the tail of the arrow represents the south pole. So we see that the compasses align themselves along the magnetic field lines. If you were ever asked to sketch the shape of the magnetic field around a bar magnet, then the kind of shape you would draw would be similar to what these iron filings trace out. I'll sketch a few of them just for illustration purposes. Outside the magnet, the direction that the arrows should point will be away from the North Pole and toward the South Pole. If you were to sprinkle filings on top of the magnet, you would also see there would be magnetic field lines that run along the magnet, like this. What I want you to see about these magnetic lines of force is that they form closed loops on themselves so that there's never a break in a magnetic line of force. Inside the magnet, you could imagine one great big long arrow whose tail is at the South Pole and whose tip is at the North Pole. So inside the magnet, the tail of the arrow represents the South Pole and the tip of the arrow represents the North Pole. Outside the magnetic field lines point away from the North Pole and towards the South Pole. This is an important difference between electricity and magnetism. In electricity, you see that lines of electric force originate on positive charges and terminate on negative charges. There's a beginning and an end of an electric line of force. On the other hand, for magnetic lines of force, the magnetic lines of force never have a beginning or an ending. They always form closed loops. We say that magnets form dipoles, whereas electric charges can be considered monopoles. Pole is really not a good term to use in the case of electric charges. When we say that magnets form dipoles, what we mean is that you never find a magnetic pole isolated by itself. It always comes with the other type of pole somewhere nearby. It is possible to separate a positive charge from a negative charge. So I could hold a proton in one hand and I could hold an electron in the other hand and separate them as far from each other as I want to. That is not possible with magnetic poles. I can't take a north pole in one hand and a south pole in the other hand and have them isolated. So you'll hear people say there's no such thing in nature as a magnetic monopole. When they say that, what they mean is that you always find the magnetic poles in pairs. What I'd like to do now is a simulation showing how a compass would behave around a bar magnet. In this simulation, there is a bar magnet and a compass needle, and the colors on this particular simulation, red stands for north magnetic poles and white stands for south magnetic poles. There are a whole bunch of compass needles that simulate iron filings around this magnet. So if I were to take this compass and to move it around, what you would see is that the needle of the compass is going to align itself in a direction that's tangent to magnetic lines of force. So you could imagine these small compass needles that are out here being iron filings tracing out the shape of the magnetic field. This is due to a permanent magnet. We've got to distinguish between a permanent magnet and an electromagnet. If electric motion of electricity, moving electricity, causes magnetic fields, in a permanent magnet we can imagine that motion being the motion due to the electrons that are in the different atoms that make up the magnetic material. At some point we'll have to ask the question, why is it that some elements and compounds show permanent magnetism whereas others don't? Because all substances have electrons that are moving, but not all substances exhibit permanent magnetism. We'll discuss that topic in a later lesson. A hint of coming things, it has to do with specially shaped electron orbitals, and the motion of those electrons is very specific. This is for a bar magnet. I'm going to show an electromagnet. So here's an electromagnet, a coil of wire that has charge motion. And in this charge motion, you're seeing electrons that move away from the negative terminal of the battery, which is black in this simulation, and around a coil of wire there are 1, 2, 3, 4 loops of this particular coil, and back towards the positive terminal of the battery. And if I move the magnet around this coil, you'll see that there's a magnetic field that is traced out of it. This is something that you'll do in the laboratory. At some point, you will have the opportunity to move compass around current carrying wires or to sprinkle iron filings. This is a DC source of electricity. I can also show an AC source. So in an AC source, the electrons move back and forth, and as they move back and forth, the direction of the magnetic field changes as a result of the change in the charge motion. We're back to the DC now, and again to the bar magnet. It was suggested at one time that the Earth itself behaves as if there's a big magnet that's buried inside. So I'd like to illustrate that. I have here a model of the Earth. If I take a compass on the surface of the Earth and align it so that the red needle points north, which we call the north pole of the compass, if in fact it is being aligned by some external magnetic field, say due to this bar magnet, as if it's buried inside the Earth, then the magnetic pole that's in the northern hemisphere must be a south magnetic pole to attract the north pole of this compass. And likewise, if I take the compass to the south geographic pole, then the south pole of that compass is attracted, so there must be a north magnetic pole that is buried in the southern hemisphere of the Earth. That will be something that you are probably not going to see on the AP exam, but you ought to be aware that the Earth's magnetism is aligned in such a way that the names of the poles of the magnet themselves and the names of the geographic poles are opposite to each other. The compasses were discovered first, north and south were known geographically, and it was only later that people developed the model of opposites attracting and likes repelling, and as a result of that, we have the notation the way that we do.